Hey everyone, welcome back with your TA with another review on before your finals. I apologize for the lateness of this review on aromatic subs. This might be my last video for the semester. Apologize for lateness because I was studying for my own test. And yeah, I just want to give you guys a final review before end of semester. Hopefully you guys do well in your finals and good luck. Yeah, so let's get started. We just do aromatic subs today, both the nucleophilic version and electrophilic version. So we both have everything. Let's get into it. Yeah, so first thing we're going to do is get into identify aromatic compounds, and then we can go into electrophilic substitution, nucleophilic substitution, and elimination addition, which is just a special version of nucleophilic substitution. You guys should be pretty much reviewed almost completely done. I just want to hopefully I could help you understand more so that you don't have to cram everything into your note sheet. So yeah, let's get into it. So aromatic and anti and non-aromatic is going to be part of your test, and you have to be able to identify each one. So here are the conditions. Aromatic conditions are that it must be cyclic, and it must be sp2. All of them must have sp2, meaning there must be uh a pi orbital in each place, a place where the electrons go around, could conjugate. So right, it must be conjugate, aka also must be flat, right? Like flat Earth. Um, Another thing is that the most important thing that specifies this aromatic condition is that it must be 4n plus 2. 4n, the n as in the pretty much the number of electron must have this sort of formula so that this n, any n you pick, as long as it reaches that number, should be able to be aromatic. So for example, 6. 6 minus 2 is 4. 4 divided by 4 is 1. So n equals 1. So it's a whole number. So it works. So it's aromatic, right? So as long as it's that number. So like, for example, 6 or 10, right? Continue like that. While anti has the same two conditions where it was cyclic and it must have sp2, right? It must also have a pi conjugate system, right? And but the only difference from aromatic and anti is that anti-aromatic has is 4n, right? And the reason why it's called anti is because there's anti-bonds when you draw out the anti-bonds. Um, and it should have anti-aromatic, anti-bonding orbitals that's filled. So for example, if we draw aromatic, for example, a benzene ring, like so, and we will draw anti-aromatic, which is this cyclo butane, with two double bonds. So what's going to happen is if we draw it in a circle, right? And we always want to have at the bottom a peak at the bottom. So it's like this. Ignore my bad drawing. But at each point that touches the circle should be an orbital, right? And so there's two pairs of degenerate orbitals. Degenerate means the same level. So you see how these are on the same level? So they're degenerate. They're pairs of degenerate. So there's two pairs, right? And there's two lone orbitals, right? So how we're going to fill this in is that there's 2, 1, 2, 3. So that's 6 electrons in total because each bond is 2 electrons. And we're just going to go from bottom up. So it's going to go 1, 2, 3. Remember, you have to alternate. 4, 5, and 6. And remember, this bond here is where you make a decisive line, where above it is anti and below it is bonding, right? And for this guy, although he's anti, if we were to draw a circle for him with a point at the bottom and drawing a circle and drawing this, and this, and we were to cut in half, uh, let's fill it in just for the speed writing this like this. These two are actually non-bonding orbitals because they're on the line. So there's definitely gonna be questions like that. And sometimes they have a 7 ring, 7 version of it, like so, making a circle, where this would be the cutoff. And you have to know if it's anti-bonding or not anti-bonding based on where it is, right? And be sure to read the question carefully because they could ask for orbitals or they could ask for electrons. So be sure to read carefully. So yeah, that's pretty much on the molecular orbitals, which is going to be like 1 or 2 questions. So it's not too hard. So you don't have to study about it as much as you do with the rest of these slides. So that's why I didn't make a slide for these. Yeah, so let's continue. Oh, remember, non is the one that's anything that's linear and not cyclic. So for example, if it's not cyclic, it's not aromatic, right? So if it's not in a circle, it's not aromatic. So for example, this is not aromatic for sure. And this is cyclic, but it has HH, which is sp3, which is not flat. So it's neither anti nor aromatic because it doesn't fill those conditions, right? So let's continue. And so here we are with example problems that we could do. An example for the first one, let's see if it's aromatic or not aromatic. So I'll do it. I'll give you like 5 minutes. You could pause it on your own and figure out each one. And I'll be going over it like right now. So yeah, so right now there's 2 hydrogens, 2 lone pairs here, and there's bond here, which is 4, and this is 6. So that's 6 electrons, meaning it falls under 4n plus 2 rule. So it's aromatic. And just to make sure it's cyclic, perfect. And it's also sp2. And because there's no double bond attaching the N to the thing, that means this N's lone pair is part of the pi system, right? And in this case, there's no lone pairs here, right? That makes this guy sp3, so he's no longer flat. So that's why he's a non, right? Same thing here. This lone pair is part of the system because there's no double bond attaching it, right? There's no double bond attaching it. So this is part of the system, okay? So now because it's part of the system now, it's 2, 4, 6, which is, like I said before, aromatic. And in this case, it's sp3 again, which is more obvious than this one, right? So because it's the sp3, it's non, because it can't be anti either, right? And in this case, it's 1, 2, 3, 4, 5, which all of them have 2 electrons, so it's 10 electron total. And that still falls under 4n plus 2, so it's aromatic. This one's 6, so it's aromatic. And this one's 8. And see how it's cyclic? And all sp2, that makes it anti. And see how this one's also cyclic, and it's 4, which is also anti because it follows the 4n rule. Make sense? Cool. Let me just clear my drawing and we can continue. So now let's get to electrophilic aromatic substitution, right? Electrophilic meaning it's an electrophile. So basically, in this case, the things that you're adding to it would be electrophiles, and the benzene's ones that's going to be attacking whatever you're adding to it, right? So what I'm saying now is that the reactants are your electrophile, and your benzene's your nucleophile, hence aromatic substitution, electrophilic aromatic substitution, because you're adding electrophiles, right? And this usually requires acid catalyst. Basically, you're going to make it a good electrophile because benzene, as we know, it's not really a good nucleophile because it's not really negative and doesn't have really too much electron to attack because its electrons are in the aromatic ring. So you want to make it attack by making it a good electrophile, the reactants, right? So you're going to add some sort of acid to it, be it like AlCl3, though that's an example of acid catalyst. So these are 6 main ones you have to know. Of course, you have to know more. For example, the TDBMS one, where you change the O into a good leaving group. Which I believe you guys could view on your own, but I'm just going over the 6 main one, which is chlorination, bromination. And of course, they happen in pairs. Uh, for the chlorination bromination is Cl2, Br2. These two are together. Nitration and the sulfonation, nitration NO3 and sulfonation SO4, and those two are in pairs. Phytocraft acylation and phytocraft alkylation are both also in pairs. Just remember that the alkylation is this one and acylation is this one. We will get into more about the parameter directors more in details later on. And just keep in mind that this guy is able to rearrange. So for example, if I have it like Cl like this, where Cl is here, right? For example, uh, this positive charge, when you make it a positive charge, later on we'll show you how it becomes positive charge. It could rearrange to a more stable version of this. So basically, when it attached to a benzene, it will attach here instead of at the end. So if you want to attach a long chain at the end, you need acylation, which is a good point to make out now. So yeah, let's get into more into the pattern so you don't have to memorize it and put on your note card, because I don't want you guys to put this on your note card. I want you guys to know the mechanism so that you guys don't have it on cheat sheet and fill up space, right? So yeah, let's continue. So this is the main pattern, right? You have an H, and you're gonna break that. So key bond broken, CH. You can break that bond, and you're pretty much gonna add electrophile to it. Remember, and you see how this is electrophile, and right under is the Lewis acid. So keep in mind this pattern: electrophile on top, Lewis acid on bottom, right? And this is gonna happen for all 6 reactions. So for example, the first step always is gonna be electrophile reacting with a Lewis acid. So for chlorination and bromination, you will use AlCl3 or FeBr3 in case of bromination. So what's going to happen is, of course, the Cl attaches and to the Al, because Al is metallic, right? And now you have a weaker Cl-Cl bond, and what's going to happen is this thing will break off, and you're going to have a Cl plus, which is a good electrophile to attack with the benzene ring. And for nitration and sulfonation, right now we're doing with sulfur, but the nitration should also be very, very similar, where basically so let's say the NO3 is in this case where the SO3 is here. So they're basically going to do the same thing where they can accept an H, and it's going to make a positive charge electrophile again, which allows the benzene ring to attack it, right? And in acylation and alkylation, right? The Cl or sometime in some cases you guys do see the occasional O O bonded O like this. In some cases, right? Where this O gets detached instead of Cl, right? So it follows the same rule. It just looks different, but it follows the same pattern, right? Organic chemistry is mostly about pattern and recognizing charges, right? And in this case, we're making another positive charge. And you could leave it as it is here, or you can make it into acylium ion. Preferably, people do like it this way because it's more stable, because the positive charge is, of course, on oxygen. And remember, this is all the first step. First step, of course, reacting with the Lewis acid. Just make sure you know which one's Lewis acid. Of course, by the notation, you should know that as well. Yeah, so let's continue. And here is a chart of the electrophile and the Lewis acid. This you guys should pretty much know and understand, which is okay. You can also copy this down so it doesn't take up as much space on your note card. Oh yeah, make sure you I'll give you what you need on your note card, because they might not have this for you on the cover sheet. Actually, they don't have it on your cover sheet. So make sure you have what I tell you to put down on your cover sheet later. Yeah, but these are for you to understand what's gonna happen. Yes, so here we go. here is the reaction in general, and please make sure you have this on your note card if you're gonna put something in your note card. Because although we did have this on our cover sheet for our exam, guys are not gonna have it as they release a cover sheet already. So please make sure this is on your note card if you do need this for substitution, right? And this has everything on how it's gonna work. Anyways, let's continue. So the second step, of course, is once you form a good electrophile, is that the benzene ring is attacked. In this case, this is the acylation, alkylation, which is gonna form a positive C carbon here, and it's gonna prompt the benzene ring attack. And note how in the electrophilic aromatic substitution that you form a cation, right? And so because you form a cation, you want to replace it again with the third step with deprotonating the H to give you back your regenerating aromatic compound. So you're regenerating the arrow. So those are the only three steps that you need. And as long as you know these three steps, you do almost any of these electrophilic aromatic substitution. And now we get to the directors, right? So para-ortho directors are usually electron donating, with the exception of F, Cl, Br, and I, which has some electron withdrawing properties. But of course, they still electron donate because they have electrons. The meta-directors are all electron withdrawing group. So just keep in mind that these are electron withdrawing groups and they're meta-directors. And we'll get into more into why they're meta-directors and ortho para-directors in the next slide. But make sure you also have this down on your note card as well, because they don't provide for you either. Yeah. So yeah, let's get into it. Why it's para-ortho director or meta-director. So let's say, for example, we have OCH3, right? Of course, as OCH3 is that you are an electron donating group. So you have lone pairs here that would gladly come down and donate down to make a double bond with O, right? And because it donates down, this bond right here now must move. So as it moves, it could immediately attack, right? Or it could continue its journey, right? But if it immediately attacks, it would form a bond here, which is your ortho position, right? If it continues its journey, then it pushes down, makes a double bond here, and now this double bond must move. And if it moves, it could continue the journey, of course, or it could attack. If it attacks here, it will be a para, right? And of course, para would be the most optimal position because of sterics. Because if it were to do ortho, it would be right next to the electron donating group, which is kind of hard to put it next to. So you don't want to put it next to it because of sterics. So if you have a chance to put it para, you always want to put it para. So anytime you want to force it ortho, you want to use sulfonation, which is SO3, because this is the one that's reversible, right? So that's why you have ortho and para. That's how ortho and para directors come to play, right? And now let's talk about meta-directors. For example, this ketone suite, right? This is electron withdrawing. So what do I mean by that? Is that this double bond can now just go up, right? And because it could go up, this oxygen becomes negative. This place becomes very positive, right? And remember, in an electrophilic aromatic substitution, this benzene acts like a nucleophile. If it's a positive charge here, will it attack at that place? No. So hence why it won't do a para or ortho directing, because if I continue to redirect the positive charge, right? The positive charge goes all the way around, and it could be at any position with a para and ortho. Hence why electron withdrawing groups don't really make it into a para or ortho position, and that's why they have it at meta position, which are these two. Make sense? And make sure that these directors only happen if the substituent is already on the ring, right? So if this guy's already on the ring, he's going to be doing the directing, right? And so if you have multiple substituents, they're going to all be directing at the same times. So for example, if I have a methyl group, right? and I have a methyl group here on the meta position, right? These two are right now in non-competition with each other, so that's great because they both want it here, here, and here, right? Because he wants it here, but he wants it here, and he wants it here. So they do have a little bit sort of competition, but not as much, where they do agree on some places, right? But here's where the problem is. Let's say if you do synthesis, where you add some sort of R group here, like this, and you add another R group here. Well, now you have a big dilemma, right? Because now this guy is a para-ortho director, and this guy is a para-ortho director. Now he wants it here, here. This guy wants it here and here, right? But this guy, he wants it here and here. And because they're equally activating, so if we go back, they're equally activating, you can't decide which one is which. It will make a racemic mixture because now they go 50-50 on where the next position will go, right? So that's something to keep in mind for synthesis. So let's do another competition where we have a methyl group, right? A R group. And we have, um, let's say NO2, right? And that's electron withdrawing. So this guy is in competition with NO2, where he wants it in the para-ortho position. He wants it in the meta position. So who wins? In this case, the NO2 wins over. Why? Because let me clear this. Uh, let's say I were to go back, right? The NO2 is a strongly deactivated group, meaning it's a very, very strong meta director, right? And while the R group's only weakly activated, meaning it's a weak para and ortho director. So what's going to happen is because this guy's much stronger, he'll be like, I take over. So majority, the major product will end up having the next constituent in the meta position. So this is another thing to keep in mind when you do these things. So let's continue on and let's have an example of synthesis. So here's a problem with synthesis, and it says starting from this, create this compound. Well, let's think about it, right? So right now we have a para-ortho director, OCH3. This is electron donating group, right? So now you're definitely going to put something in the para position. And when we have something in para position, we look at it, oh, look, it's a long chain, right? And because it's such a long chain, we have to add some kind of acylation, right? Because remember, if it did a chain with alkylation, it would end up having the bond established here, which is not what you see here, right? You're having it at the end of the chain. So you're probably going to do acylation. So what we're going to react it first with is, let's count it, 1, 2, 3. So it's going to be 1, 2, 3, and this would be Cl. And don't forget our acid catalyst, which is ACAl, Cl3, right? Don't forget that. That will make you lose major points. And this would end up leaving you with O. Give me one sec to draw. Leave you with this, right? Now you have this. Well, now he's a meta director, right? So because he's a meta director now, we can leave him here and make him force to F here. Although it wouldn't be wrong to right now just reduce him to an R group, because OR is still much stronger than R group. But I still want to keep him around because it's much easier to not have competition, right? But he's going to force a meta, and you want it to force a meta for the F. And now for F, we want to add NO2, NO3, H2SO4, and we're going to keep going, which is going to be O, H, and NO3. right? And now you want to keep going and you can keep reducing that NO3 down. I'm not going to finish it, uh, mainly because I don't think I would have enough time. Give me a sec. So yeah, here. So you will keep going. Let me just clear this. You keep going down this path until you reach with HBF4, and that should give you F at that compound. And then you just reduce it to ZNHG to R group, and then you're done. If you have any questions, just ask me in class. I'll probably be open to talking about it with you anytime. So yeah, that's pretty much for electrophilic substitution. Let's go to nucleophilic aromatic substitution. In this case, the role is reversed, right? So now the reactants are nucleophile. So they usually have negative charge. That's how you tell it's nucleophilic aromatic substitution instead of electrophilic. And so what's going to happen here is that the benzene plus the substituents are the electrophile and leaving group. Substituents are part of the leaving group, right? And this is going to be a substitution reaction. So basically SN2. But it's not going to be SN2 conditions. It's going to be a new type of condition, right? And what's going to happen here, remember how in electrophilic aromatic substitution, it makes a carbocation? In this case, it's a carboanion intermediate, right? And this is going to be accelerated by electron withdrawing groups that are para or ortho to leaving group. And in this case, leaving groups, in terms of leaving groups, F is actually the best leaving group. We'll get into why, but keep in mind that F is way better than Cl and Br and I. We'll get into that, right? But just keep that in mind. So let's get into it. So nucleophilic aromatic substitution is basically the nucleophile is going to attack that leaving group. And basically it's going to, because it attacked, it's going to push up everything, all these bonds up to the electron withdrawing group so that we have the negative charge on the N. Although it's not shown here, it definitely, not on N, on the O, right? It's going to be the double bond here, and it's going to be the O has like a negative charge. And then it's going to push everything back down and kick off the Cl. And you see how this is a rate determining step where the nucleophile attacks. And see how Cl is not kicked out yet. Keep that also in mind when I talk about leaving groups. We'll talk about that soon enough. And see how the electron withdrawing group, which is NO2, stabilizes the intermediate, right? And we'll talk about more about how these two play a big effect into the role, right? So electron withdrawing group. So the more electron withdrawing group you have, the better, right? One electron withdrawing group's lowest, 2, 3, 3 being the fastest. So the more electron withdrawing group you have, the better. Despite, like, even if it's not in the para-ortho, not in the para-ortho position, having more electron withdrawing group is still better because it stabilizes the negative charge better, right? And if you were to have it in different positions, having it in a para-ortho position is much better than having it in the meta position. Why? Well, if I were to attack with a nucleophile, right, and we now have a negative charge here because the bond moved, and let's say this negative charge keeps moving up. You see how this now has a negative charge on oxygen, and this is very stable because of the resonance. Well, if we have it in the meta position, well, this negative charge can't really be balanced by this electron withdrawing group. Although it's still good to have electron withdrawing group, it's just not balanced. It's not there to help with resonance. So it's not as good, right? It's much better to have it in a parallel position. So leaving group, now here we go. So F is the best in this case because it's not part of the slow step like in SN2. So if we look at the bottom where it's SN2, right? You see how it happens in one step where the BR breaks off? That's the rate determining step because there's only one step. So the leaving group matters. But in this case, leaving group doesn't matter because it's a lot like E1CB where it goes up and it comes back down to push it off, right? And in this case, F is a better leaving group. Why? Because our slow step is the nucleophile attacking. And our nucleophile attacking wants not much of hindrance. It doesn't want steric effect, right? F being so small that nucleophile can attack straight through. And it's not going to be bothered by the big radius of Cl or Br or I. And another reason why is that fluorine is very electronegative. So it's okay being like okay leaving group, but not a bad leaving group. But most of the thing is on F being a little smaller so that it is less steric. when you attack it. So now let's get into elimination addition. So elimination addition, like I said before, it's a very special case of nucleophilic aromatic substitution, where you're using negative NH2. So it could be any kind of ion in front of it. So K, NH2, NH3. So NH3 is our bottom, right, of the arrow. And so this is, like I said, a special type of nucleophilic attack, and it makes a benzyne. Benzyne as in triple bonds. So keep that in mind because it has a Y, so it's triple bonded. And we'll get into more into now how it works. So step one, because this is a very basic, strong base, right? Does elimination reaction. Remember that. E2, remember? So we'll take any H's that are next to the leaving group. Remember, any H's that are next to the leaving group. So for example, we could take this H, or we could take the H over here. It's totally up to the system, right? To chance. And so what's going to happen is that it's going to take this H and eliminate Cl, the Cl based off of elimination, and it's going to form a benzyne. Well, it's not really a triple bond. It's more like you draw it like a radical, or you could draw it negative charge here and positive charge here. It's not really a benzene. Well, a benzyne, right? Because this if the triple bond was actually a real triple bond, it would be linear. They're drawing it as a benzyne because that's a way to represent it that we can understand, right? And what's going to happen is that this is so unstable that nucleophilic molecules will straight up just attack it. So our nucleophilic molecule in this case is the NH3, right? So this NH3, what's going to happen is this NH3 is just going to come in with this lone pair and attack. Boom. And now it becomes positive charge. And what's going to happen, right, is that this negative charge now, as it shifts over, right, this negative charge is just going to seal that H, hence why you have this kind of formation. And keep in mind how it makes two compounds, right? Not compounds, products, right? So if the case were that I had, let's say, a CH3 here, right? Like this, methyl group, you see how it still makes two compounds. Makes sense? It makes A and makes B. But let's say I would have, so originally this was my Cl group, right? And of course, we took the H here. But let's say we were to take the H on this side. Well, now not only can it make A and B if it were to do this triple bond, and it takes this H, if we were to take the other H, you could make it so that it would make this, right? Because now when you have a triple bond on this side, you could have NH to attach here or attach here. If attach here, you already have that product as A, right? And now you have A, B, and C. So just keep in mind where can you draw a triple bond. So a triple bond only happens when you could take an H, right? Make sense? Hopefully that makes a lot more sense with benzyne. Let's continue. And that's it. Yeah. Hopefully you guys don't have any question. Oh, ignore this. This is actually part of my theme that I use. I use slides go. So yeah, thank you.